3.4 Z-transform properties. Many of the mathematical properties of the Z-transform are particularly useful in studying discrete time signals and systems. For example, these properties are often used in conjunction with the inverse Z-transform techniques discussed in section 3.3 to obtain the inverse Z-transform of more complicated expressions. In section 3.5 and chapter 5 we will see that the properties also form the basis for transforming linear constant coefficient difference equations to algebraic equations in terms of the transform variable z, the solution to which can then be obtained using the inverse Z-transform. In this section, we consider some of the most frequently used properties. In the following discussion, x, z, denotes the Z-transform of xn, and the rock of x, z, is indicated by Rx, Le, xnx, z, rock equals Rx. As we have seen, Rx represents a set of values of z such that RRLT is LTRL. For properties that involve two sequences and associated Z-transforms, the transform pairs will be denoted as XL and XL, z, rock equals Rxj, z x2 n x2, z, rock equals Rx2. 3.4.1 Linearity. The linearity property states that AXLN plus BX2N AXL, Z, plus BX2, Z, rock contains Rxi and Rx2, and follows directly from the Z-transform definition, EQ, 3.2, i.e., 0,0,0,0,0,0 Ax n plus Bx2n, Zn equals Al11 and Zn plus Blx2 and Zn. N equals 00 n equals 00 n equals 00 dash comma dash IZE IZE Rxi Rx2 as indicated. To split the Z-transform of a sum into the sum of corresponding transforms, Z must be in both rocks. Therefore, the rock is at least the intersection of the individual rows. For sequences with rational Z-transforms, if the poles of x1, Z, plus bx2, Z, consist of all the poles of xl, Z, and x2, Z, i.e., if there is no pole zero cancellation, then the rock will be exactly equal to the overlap of the individual rocks. If the linear combination is such that some zeros are introduced that cancel poles, then the rock may be larger. A simple example of this occurs when xln and x2n are of infinite duration, but the linear combination is of finite duration. In this case the rock of the Section 3.4 Z-transform properties. Linear combination is the entire Z-plane, with the possible exception of Z0 or Z equals 0, 0. An example was given in example 3.6, where xn can be expressed as xn equals n, un, n, equals anu nn. Both anu n and anu nn are infinite extent right-sided sequences, and their Z-transforms have a pole at Z equals a. Therefore, their individual rows would both be isl gt lal. However, as shown in example 3.6, the pole at Z equals a is cancelled by a 0 at Z equals a, and therefore, the rock extends to the entire Z-plane, with the exception of ZO. We have already exploited the linearity property in our previous discussion of the use of the partial fraction expansion for evaluating the inverse Z-transform. With that procedure, x, z, is expanded into a sum of simpler terms, and through linearity, the inverse Z-transform is the sum of the inverse transforms of each of these terms. 3.4.2 Time shifting. The time shifting property is, xn rock equals Rx, except for the possible addition or deletion of Z equals 0 or Z equals 0. The quantity no is an integer. If no is positive, the original sequence xn is shifted right, and if no is negative, xn is shifted left. As in the case of linearity, the rock can be changed, since the factor z no can alter the number of poles at z0 or z equals 0, 0. The derivation of this property follows directly from the Z-transform expression in EQ, 3.2. Specifically, if n equals xn no, the corresponding Z-transform is 0, 0 y, z, equals lxn no zn. N equals 00 with the substitution of variables m equals n no, 0, 0 y, z, LXMZ dash, M plus no, M equals co-OC no LXMZ M equals OO or Y, Z, Z Knox, Z. The time-shifting property is often useful, in conjunction with other properties and procedures, for obtaining the inverse Z transform. We illustrate with an example. Example 3.14 Shifted exponential sequence. Consider the Z transform 11x, Z, equals isilk 4Z from the rock. We identify this as corresponding to a right-sided sequence. We can first rewrite x, Z, in the form 1x, Z, equals ZL, 3.56, isilk 4 feet 1 inch. This Z transform is of the form of EQ, 3.41, with M equals N equals 1, and its expansion in the form of 3.45 is 4x, Z, equals dash 4 plus 1, 3.57, from EQ, 3.57, it follows that xn can be expressed as xn-48n plus 4, rn. 3.58, an expression for xn can be obtained more directly by applying the time-shifting property. First, x, z, can be written as 1x, z, zl, 1. Isilk 4, 3.59, for z from the time-shifting property, we recognize the factor in EQ, 3.59, as being associated with a time shift of one sample to the right of the sequence, I, NUN, i.e., 1, NLXN for -1. 3.60, it is easily verified that x, 3.58, and 3.60, are the same for all values of n, i.e., they represent the same sequence. 3.4.3 Multiplication by an exponential sequence. The exponential multiplication property is z xn plus dash plus x, z slash zo, rock equals is all rx. The notation rock is all rx signifies that the rock is rx scaled by the number is all, le, if rx is the set of values of z such that rrlt is ltrl, then is all rx is the set of values of z such that is all rrlt is lt is all rel. This property is easily shown simply by substituting xn into EQ, 3.2. As a consequence of the exponential multiplication property, all the pole zero locations are scaled by a factor zo, since, if x, z, has a pole, or 0, at zzl, then x, z slash zo, will have a pole, or 0, at z equals zozi. If zo is a positive real number, the scaling can be interpreted as a shrinking or expanding of the z-plane, i.e., the pole and 0 locations. Section 3.4 Form 1.56, 1 The T57, 3.58, Fting 3.59, Ling, i.e., 3.60, they i.e., off z-transform properties change along radial lines in the z-plane. If zo is complex with unity magnitude, so that chwo zo equals e, the scaling corresponds to a rotation in the z-plane by an angle of VO, i.e., the pole and 0 locations change in position along circles centered at the origin. This in turn can be interpreted as a frequency shift or translation of the discrete time Fourier transform, which is associated with the modulation in the time domain by the complex exponential sequence Ayukht, Jn. That is, if the Fourier transform exists, this property has the form example 3.15 exponential multiplication starting with the transform pair 1. Isil GT1, 3.61, 1C1. We can use the exponential multiplication property to determine the z-transform of xn Rn cos 1, un, rgto, 3.62. First, xn is expressed as 1 New Jersey equals dash, rejwo, nu n plus dash, rejwo, New Jersey 2 then, using EQ, 3.61, and the exponential multiplication property, we see that 2 underscore, rejwo, nu n isil gtr, 1 rejwo's 111. 2 erchwo, nu n isil gtr.2 rejwo's 1 from the linearity property, it follows that 1xz equals dash 1 dash underscore dash 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 7 dash 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 colon colon plus 1 2 is GTR 3.63 1 is GTR 1 dash 2 R 3.4.4 differentiation of x z. The differentiation property states that nxn rock equals Rx. This property is verified by differentiating the z-transform expression of EQ 3.2, i.e., for 00x, z, equals Lxnzn, n equals 00. Chapter 3 The L transform we obtain OC dx, z, zl, n, xnznlzn equals OOL00 nxnzn equals znxn. N equals 00. We illustrate the use of the differentiation property with two examples. Example 3.16 Inverse of non-rational z-transform. In this example, we use the differentiation property together with the time-shifting property to determine the inverse z-transform considered in example 3.12. With x, z, log, L plus az1 is gt lal, we first differentiate to obtain a rational expression, dx, z, dz from the differentiation property, az1 nxn is lal, 3.64, 1 plus azl. The inverse transform of EQ, 3.64, can be obtained by the combined use of the z-transform pair of example 3.1, the linearity property, and the time-shifting property. Specifically, we can express nxn as nxna, n lu n1. Therefore, nzxn earn minus 1 plus dash plus log, 1 plus is lal. And the result of example 3.16 will be useful in our discussion of the Sepstrum in chapter 13. Example 3.17 Second order pole. As another example of the use of the differentiation property, let us determine the z-transform of the sequence xnnaunn, anu n. From the z-transform pair of example 3.1 and the differentiation property, it follows x, z, that c underscore cl, is gt lal daz1 is gt lal, 1. Section 3.4 Z-transform properties. Therefore, is a gt lal 3.4.5 conjugation of a complex sequence. The conjugation property is expressed as x New Jersey x, z asterisk, rock rx. This property follows in a straightforward manner from the definition of the z-transform, the details of which are left as an exercise. Problem 3.54. 3.4.6 Time reversal. The time reversal property is given by z1xnx, 1/z, rock rx. The notation rock equals llrx implies that rx is inverted, i.e., if rx is the set of values of z such that rrlt is ltrl, then the rock for x, llz asterisk, is the set of values of z such t bat llrllt is ltlrr. Thus, if zo is in the rock for xn, then liz is in the rock for the z-transform of x asterisk n. If the sequence xn is real or we do not conjugate a complex sequence, the result becomes xnx, liz, rock equals 1 rx. As with the conjugation property, the time reversal property follows easily from the definition of the z-transform, and the details are left as an exercise. Problem 3.54. Note that if zo is a pole, or 0, of x, z, then 11 zo will be a pole, or 0, of x, liz. The magnitude of zo is simply the reciprocal of the magnitude of zu. However, the angle of 11 zo is the negative of the angle of zu when the poles and zeros of x, z, are all real or in complex conjugate pairs, as they must be when xn is real. This complex conjugate pairing is maintained. Example 3.18 Time reversed exponential sequence. As an example of the use of the property of time reversal, ians either the sequence xn equals a lu n, which is a time reversed version of a lu n. From the time reversal property, it follows that x, z, equals. Note that the z-transform of a lu n1 has a pole at z equals a, while x, z, has a pole at l/a. 133.4.7 Convolution of sequences according to the convolution property. z xln asterisk x2n plus dash dash plus xi, z, x2, z, rock contains rxln rx2. To derive this property formally, we consider 00ynl equals lxd kx2n kj, k equals 00 so that y, z, equals L00 YNZNN equals CCN fu Lxt KX2 NKI. If we interchange the order of summation, which is allowed for Z in the rock, 0000 Y, Z, equals LXT LK LX2 NKZ NK equals 00 N equals 00. Changing the index of summation in the second sum from N to M NK, we obtain Y, Z, equals KX IK MXX2 MZMI equals FXLKZK equals F11 KZK, X2, Z, K equals 00 is Ali Rx2 K equals 00. Thus, for values of Z inside the rocks of both XL, Z, and X2, Z, we can write Y, Z, equals 11, Z, X2, Z, where the rock includes the intersection of rocks of XL, Z, and X2, Z. If a pole that borders on the rock of one of the Z transforms is cancelled by a zero of the other, then the rock of Y, Z, may be larger. The use of the Z transform for evaluating convolutions is illustrated by the following example. Form Section 3.5 L Transforms and LTI Systems. Example 3.19 Convolution of finite length sequences. Suppose that XLN Sn plus 2 Snt plus Sn2 is a finite length sequence to be convolved with the sequence x2n equals sen Sn1. The corresponding Z transforms are XL, Z, 1 plus 2 ZL plus Z2 and X2, Z, equals 1 ZL. The convolution yen xln asterisk x2n has Z transform Y, Z, equals XL, Z, X2, Z, equals 1 plus underscore Z2. Since the sequences are both of finite length, the rocks are both isogt0 and therefore so is the rock of Y, Z. From Y, Z, we conclude by inspection of the coefficients of the polynomial that yen equals sen plus Sn minus 1 Sn minus 2 Sn3. The important point of this example is that convolution of finite length sequences is equivalent to polynomial multiplication. Conversely, the coefficients of the product of two polynomials are obtained by discrete convolution of the polynomial coefficients. The convolution property plays a particularly important role in the analysis of LTI systems, as we will discuss in more detail in section 3.5 and chapter 5. An example of the use of the Z transform for computing the convolution of two infinite duration sequences is given in section 3.5. 3.4.8 Summary of some Z transform properties. We have presented and discussed a number of the theorems and properties of Z transforms, many of which are useful in manipulating Z transforms in the analysis of discrete time systems. These properties and a number of others are summarized for convenient reference in Table 3.2. 3.5 Z